This video is on RMS value, and RMS stands for root mean squared. So this acronym here, the R is root, the M is mean, which is, as you know, same thing as average, and then the S is square. And the whole purpose of RMS is that this value is sort of an average value for symmetrical waveforms, and I'll get what I mean by sort of here. So in circuits, as we've already discussed, a common waveform or signal is a sinusoidal signal, either cosine or sine. So I've written a cosine function here for v of t, and as you know, a sinusoid is a symmetrical function that it's going to have equal area above and below its center point. So you see, one way to describe the magnitude of a sinusoidal signal is just with its peak value or its amplitude, which is this a value here, like we've seen. Remember, this value is the value from either the positive peak to the center point or the negative peak to the center point. And then you also have peak to peak, which is just from the positive peak to the negative peak. And we can get the value of this waveform at any instant in time, right? So this is a good way, you just plug in your particular time value here along with what the amplitude is and the frequency and the phase angle, and that will yield an instantaneous value along that waveform at that particular t. And that's fine. But sometimes it's useful to have a value that's over an interval of time. And the most common value like that is an average value where, as you learned in your calculus, you just integrate over a period of time. Right? You integrate the function over a period of time, and then you divide by that same period of time. Okay, that's your basic definition of an average value from calculus. But as you know, if I were to have two different sinusoids, like say I have this cosine that's very small in amplitude, and I have this cosine that's much larger than this cosine in amplitude. Well, you can tell by just looking at the waveforms that they're not the same. I mean, clearly one's a lot larger than the other. However, if you took the average value of this small sinusoid centered around 0, well, it would just equal 0, right? Because it's a symmetric waveform. The positive areas would cancel out the negative areas. Likewise, the average value of this much larger sinusoid would also be 0, right? Because again, the positive areas would cancel out the negative areas. So you see, a straight average isn't useful. It doesn't yield useful information as far as describing the differences in these two waveforms, because clearly, again, they're not the same waveform, but the average value would have you think that they're the same, since the average value for both are 0. So you see, that's where RMS comes in, because RMS is a way to get a value that's over an interval of time for a symmetrical waveform, but it's going to be more descriptive. Okay, so when you get the RMS value for a waveform, before you take the average, you square the function. So this is actually the first operation in the RMS, is that you square the value. Then the second thing you do is you take the average, and then after you take the average, you take the square root. Okay, so the operations performed are right in the acronym. It's just the opposite. We say RMS value, but the operation is actually square, then take the mean, then take the square root. So if you take our cosine function here and perform these three operations, and on Polylearn I have a handout that shows you the details of the derivation. So you see how we're starting here, that we square our function, so we got cosine squared, a squared, and then we're taking the average, so that's the 1 over the period, integrating over the same period, and then we square root. So if you go through, as you can see here, the end result is what you see at the bottom of this handout, that the RMS value, and sometimes RMS is called effective, okay, effective values. So you might want to write, if you're taking notes along with this video, that RMS sometimes is called the effective value. Okay, so for a symmetrical, or excuse me, for a sinusoid centered on 0, the RMS value is just equal to the peak value divided by root 2. Okay, so again, if you go back, that was the result of this derivation here. You go through all this work, and here's the key result. So now, if I have this small waveform here, this small cosine, and say the peak value is 1 volt, and here in this waveform the peak value is 10 volts. Okay, again, peak being from the center point up to one of the peaks, right? So this distance right here. Well, now I do have a value that's descriptive, that gives me information, because I can clearly see that these this waveform is much larger than this one, and now with this value I know it's 10 times greater than that one in amplitude. So the RMS value will reflect that the RMS for this small amplitude sinusoid would be 1 over root 2, and the RMS for this much larger, in fact 10 times larger sinusoid, well, its RMS value is 10 over root 2. So you see, that's what I mean by that RMS is sort of an average value for symmetrical waveforms, because if you were to take a straight average, you wouldn't get any meaningful information. But with this definition, and by performing these operations, we now obtain a value that is descriptive over time. Now, for those of you that are taking the lab portion of the course along with the lecture, another important thing to know about RMS values, that AC voltmeters and AC current meters. Okay, so AC voltmeters that you use in the lab, and also ammeters. Okay, they display RMS. So when you're using one of these pieces of equipment in the lab, and it displays some number on its faceplate, in the front, the display, those numbers are RMS. Okay, so we will on occasion be using RMS values in the course, for homework problems and analysis and such, and especially when we get to AC power, we tend to use RMS values in those types of problems.